When life evolved on this planet, it was probably using abundant sources of energy that were already on the planet. There are organisms that can use, for example, hydrogen gas as an energy source, the same way we use sugar. And probably early life was using those types of things, whether it's minerals where they can get high energy electrons. All we really do with sugar is extract high energy electrons from it, put them into an electrical circuit and do things like make ATP, run, all the things we do. Essentially, we're electrical organisms. And it really doesn't matter where the electrons come from. We can only get them from carbon-carbon and carbon-hydrogen bonds. There are organisms on the planet today that get them from other things, like minerals, from hydrogen and so forth. Maybe the first life on the planet primarily wasn't using the things we used, like carbon-carbon and carbon-hydrogen bonds, but was rather using things like hydrogen. But that wasn't sustainable. There's only so much high-energy stuff on the planet to begin with, so a key thing that happened that made it possible for us to be here is at some point, and it's on the timeline, that organisms evolved this ability to do photosynthesis, specifically the ability to split water. Because now what you have organisms doing is they don't need to, they can make their own high energy electrons with sunlight. So the essence of photosynthesis is to split water, to take its electrons and use the energy of sunlight to push them up to high energy. And once you have high energy electrons, whether you're a chemical company wanting to make products or you're an organism, if you have high energy electrons, you can do all the things you need to do. When photosynthesis evolved, two really major things happened. One, over geological time, there's been a heck of a lot more photosynthesis than respiration and combustion. That's where all the oxygen on this planet comes from, is that imbalance. And the corollary to that is the levels of carbon dioxide in the atmosphere have been decreased by that imbalance of photosynthesis and respiration. So a lot of the stuff that would be carbon dioxide in the atmosphere is now buried in soil as organic matter or down deep as fossil fuels or that type of stuff. So the evolution of photosynthesis really changed this planet in remarkable ways. I guess another way it changed is that the things that had been fuels for life on the planet can't exist in the presence of oxygen. So if you had organisms living off of hydrogen, because there was a lot of hydrogen in the atmosphere, once you put oxygen in the atmosphere, the hydrogen's gone. It reacts with oxygen and turns into water. Or many of the minerals that organisms might have been using, they get oxidized. They're no longer food anymore for organisms. So now most ecosystems are based on photosynthesis, except for rare ecosystems where oxygen doesn't get to. So there's still organisms in some parts of our planet living off of minerals, for example, but they tend to be some places deep buried, for example, under ice, where oxygen isn't destroying the minerals that they need to survive. You know, if you think about that timeline, once we get into the 450 million years ago, well, we're in the last 10% of our timeline already, right? Obviously, all fossil fuels came after photosynthesis. I mean, it is possible that some fossil fuels were actually created by organisms using something other than photosynthesis. You go back 3 billion years, and there were a group of bacteria called methanogens that were really abundant on Earth, converting hydrogen into methane. So they used hydrogen as their energy source. They actually, we use sugar when we convert it to carbon dioxide. They were taking hydrogen and converting it to methane. And it's possible that some fraction of fossil fuels are actually due to these other organisms that were using a different source of energy, because they were taking hydrogen, converting it to methane, but they were also building themselves, right? So their remains could be part of fossil fuels. It doesn't have to be all photosynthesis, but certainly most of it probably is. Photosynthesis really about, and it's an estimate, a guess, somewhat of a guess, but probably about 3 billion years ago, photosynthesis started to take over most ecosystems. So it's been ongoing. But you only get fossil fuels in ecosystems where for a time there's a great imbalance in the process, right? So the most recent example of this is the Carboniferous period. That was just about 300 million years ago, you know, a real drop in the bucket on the timeline. So in the Carboniferous period, that's when coal was being laid down for the most part. So the coal deposits we're using are from the Carboniferous, and there were a lot of the land mass was incredibly productive, swampy areas where the plant growth outstripped the ability of other organisms to use those plants, and all the plant material was getting buried. West Virginia, for example, in the Carboniferous was an equatorial swamp. So, you know, in 300 million years, West Virginia moved from the equator as a swamp into a mountainous region. So there's been a lot of changes, but that particular fossil fuel, West Virginia coal, is 300 million years ago. Some of the oil deposits are certainly from a much earlier era. So it depends on the fuel and the deposit we're looking at. At one point, the most abundant organism on Earth before photosynthesis was probably this group of organisms called methanogens, because there was a lot of hydrogen. You know, hydrogen is really abundant stuff in the universe. After the Big Bang, the entire universe was hydrogen. Right, so our sun is hydrogen, or it's used to be all hydrogen. Now a fair amount of it has been converted to helium, but there's still a lot of hydrogen left. So on early Earth, hydrogen was pretty abundant. And so, as I said, there were these organisms using hydrogen as an energy source. And since it was abundant and it was in the atmosphere, they could get it anywhere, so they really proliferated. You go back to when the Earth was formed, the sun was nowhere near its present amount of output. So it turns out that the sun was about 70% of its present output. If we had a sun that lost 30% of its output today, the Earth would be a ball of ice. So if you go back then to 3 billion years ago, for example, then the obvious question is, why wasn't the Earth a ball of ice 3 billion years ago? Not only was it not a ball of ice, it was warmer than it is today with this faint sun. And the part of the answer is thought to be that it's because there were so many methanogens on the planet making all of this methane that the atmosphere was very enriched in methane. And methane, as you probably know, is a very potent greenhouse gas. So that in fact it was the methanogens changing the atmosphere to a methane-rich atmosphere that created a tremendous greenhouse effect and kept the Earth from freezing when the sun was faint. So that's another example of life affecting a huge aspect of the history of the planet, geologically and in many ways. But it turns out that the methanogens probably kept the Earth from turning into a ball of ice, but their ability to do so was then thwarted by the evolution of photosynthesis. Because once photosynthesis evolved, the evidence is pretty strong that this entire planet was a ball of ice. That even at the equators, that the ice could have been, by some estimates, a mile thick, even at the equators. And the reason was, again, the sun was faint. And once photosynthesis evolved, it poisoned the methanogens. Oxygen is toxic to many anaerobic microbes. It basically wiped out most of the methanogens. Some still survive in swamps in places where there's not oxygen. And methane can't exist in the atmosphere if oxygen is there. It'll react. So just as an aside, there's a lot of concerns, and rightly so, about that humans are not only adding greenhouse gases like CO2, but we're adding methane as well as a greenhouse gas. But if we stopped adding methane, the good news is that would go away in a few years. Methane just doesn't last in the presence of oxygen. They react and they turn into carbon dioxide. Whereas the carbon dioxide we're dumping into the atmosphere is going to last a long time. So the Earth went from warm, to a ball of ice, and then eventually back to, with a lot of little blips in between, the kind of planet we have now. In this era that I'm talking about, even when I'm talking about photosynthesis, it wasn't the kind of plants we're looking out the window and seeing. It was all bacteria. So bacteria invented photosynthesis. And in the types of plants that we can see out the window, they obviously have chloroplasts. But those chloroplasts were descendants of the bacteria that have invented photosynthesis. So it really was, photosynthesis was invented once by bacteria. No other organisms invented it, but how multicellular plants arose was they actually adopted these photosynthetic bacteria. But in this era where, you know, the earth froze, first it was warm, then the methanogens got wiped out and all their methane went away. It was plants, but I just want to point out the plants were bacteria living in water. They're called cyanobacteria. And it wasn't until later that we had plants with leaves and roots and that kind of stuff. If we think about what life is, it's just whoever is successful is reproducing, right? And so organisms that evolved the ability to do photosynthesis could get free energy. And if, you know, all you need is sunlight and water, and you make hydrogen and electrons, and you can flourish. So obviously when photosynthesis evolved, it was, those organisms were highly successful. Well, they were, except the problem was that once you started putting oxygen into the atmosphere, then it eliminated all the hydrogen. So just like I said, methane can't exist in the atmosphere for very long if there's oxygen, neither can hydrogen. So the early Earth's atmosphere had a lot of hydrogen, but once photosynthesis came along and put oxygen in the atmosphere, bye-bye hydrogen. Every time a hydrogen collides with an oxygen, you're going to make a water. It's just a matter of collisions and chemical reactions. Oxygen is very reactive. You know, if you leave a piece of iron outside and it gets a little moisture to help the catalysis, it's going to turn to rust, right? In the same way, hydrogen is going to turn to the hydrogen equivalent of rust, which is water. So hydrogen simply can't exist anymore. It wasn't that the cyanobacteria set out to eliminate the methanogens. It was just inevitable if they released oxygen. All the oxygen on this planet came from water. Some of it turned back into water when it reacted with hydrogen. So water is an incredibly abundant molecule in the universe. And this planet has obviously an enormous amount of it. It's not like we have more water. We actually, to get this oxygen, all the oxygen we have in the atmosphere has come at the expense of using up some water. But you don't have to use much. On a percent basis, it's almost trivial compared to how much water is on this planet to give us the 20% oxygen that we now have. But that's where it all came from. So I guess we have a little less water on the planet than when things started because of photosynthesis. I mean, if you went back, you know, 30,000 years ago, we weren't having much of an impact, but we're clearly having an impact. You've seen all the curves on how much carbon dioxide is in the atmosphere. We're close to having doubled it since the Industrial Revolution. And so we're having a major impact on the chemistry of the planet. Carbon dioxide levels have almost doubled, and it's all due to us. Obviously, if we double the amount of anything in the atmosphere, something's going to be different, right? And the something that's going to be different is the planet's going to get warmer. There's just no question about that. There are questions about exactly how much warmer, how fast, but if you double the amount of carbon dioxide, the atmosphere retains more heat, and the planet is getting warmer and will continue to get warmer with more carbon dioxide in the atmosphere. In the same way that the methanogens put a lot of methane in the atmosphere, it kept the planet warm. Carbon dioxide keeps the planet warm. I mean, some carbon dioxide is good. So the average temperature on the Earth is 65 degrees Fahrenheit. If we didn't have an atmosphere, the average temperature would be 0. So having an atmosphere is like having blankets covering you at night. And the question is, how thick are the blankets? More carbon dioxide, thicker blankets. So we've doubled the carbon dioxide portion of the blankets in the last roughly 2 centuries. Just a little blip on our timeline. That's not to say, there have been times in the history of our planet where carbon dioxide levels have been a heck of a lot higher than the doubling we're close to having. But in fact, during those times, the planet has been a lot warmer. I said the planet turned into a ball of ice, or at least most of the data indicate that, about 2.5 billion years ago. What got us out of that ball of ice was in fact volcanic activity, because volcanic activity was spewing enormous amounts of carbon dioxide into the atmosphere that may have increased carbon dioxide levels to at least 100 times what they are today, not a doubling, 100 times. And then when it all melted, the planet might have been an average temperature of 120 degrees. So why did it come back? Actually, most of the carbon dioxide wasn't trapped by photosynthesis, it was trapped by geology. So that over geological time, most of this carbon dioxide that's been in our atmosphere combines with minerals and forms carbonates, like limestone. Most of that's not biologically driven, but simply driven by carbon dioxide being sequestered by minerals in the crust of the Earth. There's different ways it's going to affect it. One is, if it gets a bit warmer and we lose all the ice on the planet, like from Greenland and polar ice caps, bye-bye Florida. The highest point in Florida, I think, is 160 feet, and that's up by the Georgia border. So, if we lose all the ice, Florida's gone, or most of it, except for a little. You can still cross the border from Georgia, but there won't be much. The concern is, if you change temperature, you'll change patterns of weather, moisture flows, and so forth. Whether we'll have more deserts, fewer deserts. There's a lot of people trying to model that and try to predict what's going on. That's pretty tough to make those kinds of predictions. Clearly, there'll be differences, though. We're not going to lose the water off of the planet, though. We have enough gravity and so forth. Mars used to have a lot of water. It's all gone. There's been different periods of fossil fuel formation in different eras in different parts of the planet. But it's wherever there's an excess of photosynthesis, where the products of photosynthesis, wood, plant material, aren't broken down by organisms. And when they get buried, then we have fossil fuels of various sorts. Whether it's, the most recent examples of fossil fuels would be peat bogs. There are parts of the world where people dig up peat and burn it. That's a really recent fossil fuel. Or whether at what point do you call it a fossil, and what point is it just recently buried plant material? It's all a continuum, right? So I don't know where you draw the line. That's the problem with most things. There's no strict line to be drawn. But if it's been buried long enough, we call it fossil fuels. And in certain geological formations that are older than coal, it's mainly oil. But even oil is not one thing, right? The oil from one part of the world is quite different than oil from another part of the world. It's not just one. Oil isn't one thing. It's a lot of things. It ranges from what refineries call sweet crude, because you can make gas out of it. You get the best yield of things like gasoline, to things like the tar sands up in Canada, which are a real mess to extract fossil fuels from. But they're being mined because it's close to the surface. So they've found, technology's been developed to deal with tar as a fossil fuel.